A hierarchy is an arrangement of items in which the items are represented as being above, below, or at the same level as one another. A hierarchy can link entities either directly or indirectly, and either vertically or diagonally. The only direct links in a hierarchy, insofar as they are hierarchical, are to one's immediate superior or to one of one's subordinates. Although a system that is largely hierarchical can also incorporate alternative hierarchies, indirect hierarchical links can extend vertically, upwards or downwards via multiple links in the same direction, following a path. All parts of the hierarchy which are not linked vertically to one another nevertheless can be horizontally linked through a path by traveling up the hierarchy to find a common direct or indirect superior, and then down again. This is akin to two co-workers or colleagues. Each reports to a common superior, but they have the same relative amount of authority. Organizational forms exist that are both alternative and complementary to hierarchy. Heterarchy is one such form. Nomenclature. Hierarchies have their own special vocabulary. These terms are easiest to understand when the hierarchy is diagrammed. In an organizational context, the following terms are often used related to hierarchies. Object. One entity. Dimension. Another word for system from online analytical processing. Member. An in or a tiny. Rank. The relative value, worth, complexity, power, importance, authority, level etc. of an object. Level. A set of objects with the same rank or importance. Ordering. The arrangement of the hierarchy. The arrangement of a particular set of i.e. multiple hierarchies are possible per collection. All of the objects at one level. Superior. A higher level or an object ranked at a higher level. Subordinate. A lower level or an object ranked at a lower level. Hierarch. The top level of the hierarchy, usually consisting of one object or member of a dimension. Peer. An object with the same rank. Neighbor. The adjacent level, ranking. Interaction. The relationship between an object and its direct superior or subordinate. A direct interaction occurs when one object is on a level exactly one higher or one lower than the other. Distance. The minimum number of connections between two objects, i.e., one less than the number of objects that need to be crossed to trace a path from one object to another. Span. A qualitative description of the width of a level when diagrammed, i.e., the number of subordinates an object has. In a mathematical context, the general terminology used is different. Most hierarchies use a more specific vocabulary pertaining to their subject, but the idea behind them is the same. For example, with data structures, objects are known as nodes, superiors are called parents and subordinates are called children. In a business setting, a superior is a supervisor, boss, and a peer is a colleague. Degree of branching. Degree of branching refers to the number of direct subordinates or children an object has a node has. Hierarchies can be categorized based on the maximum degree, the highest degree present in the system as a whole. Categorization in this way yields two broad classes, linear and branching. In a linear hierarchy, the maximum degree is 1. In other words, all of the objects can be visualized in a lineup, and each object has exactly one direct subordinate and one direct superior. Note that this is referring to the objects and not the levels. Every hierarchy has this property with respect to levels, but normally each level can have an infinite number of objects. An example of a linear hierarchy is the hierarchy of life. In a branching hierarchy, one or more objects has a degree of 2 or more. For many people, the word hierarchy automatically evokes an image of a branching hierarchy. Branching hierarchies are present within numerous systems, including organizations and classification schemes. The broad category of branching hierarchies can be further subdivided based on the degree. A flat hierarchy is a branching hierarchy in which the maximum degree approaches infinity, i.e., that has a wide span. Most often, systems intuitively regarded as hierarchical have at most a moderate span. Therefore, a flat hierarchy is often not viewed as a hierarchy at all. For example, diamonds and graphite have flat hierarchies of numerous carbon atoms which can be further decomposed into subatomic particles. An overlapping hierarchy is a branching hierarchy in which at least one object has two parent objects. For example, a graduate student can have two co-supervisors to whom the student reports directly and equally, and who have the same level of authority within the university hierarchy. Pseudo-Dionysius used the related Greek word both in reference to the celestial hierarchy and the ecclesiastical hierarchy. The Greek term, epsilon rho alpha rho chi iota alpha, means rule by priests, and Dionysius is credited with first use of it as an abstract noun. Since hierarchical churches, such as the Roman Catholic and Eastern Orthodox churches, had tables of organization that were hierarchical in the modern sense of the word, the term came to refer to similar organizational methods in secular settings. Visualization. A hierarchy is typically depicted as a pyramid, where the height of a level represents that level's status and width of a level represents the quantity of items at that level relative to the whole. For example, the few directors of a company could be at the apex, and the base could be thousands of people who have no subordinates. These pyramids are typically diagrammed with a tree or triangle diagram, both of which serve to emphasize the size differences between the levels. An example of a triangle diagram appears to the right. An organizational chart is the diagram of a hierarchy within an organization, and is depicted in tree form below. More recently, as computers have allowed the storage and navigation of ever larger data sets, various methods have been developed to represent hierarchies in a manner that makes more efficient use of the available space on a computer's screen. Examples include fractal maps, tree maps and radial trees. Visual hierarchy. In the design field, mainly graphic design, successful layouts and formatting of the content on documents are heavily dependent on the rules of visual hierarchy. Visual hierarchy is also important for proper organization of files on computers. An example of visually representing hierarchy is through the nest structure. The nest structure represents hierarchical relationships by using layers of information. The child element is within the parent element, such as in a Venn diagram. This structure of representing hierarchy is most effective in representing simple relationships. For example, when directing someone to open a file on a computer desktop, one may first direct them towards the main folder, then the subfolders within the main folder. They will keep opening files within the folders until the designated file is located. For more complicated hierarchies, the stair structure represents hierarchical relationships through the use of visual stacking. Visually imagine the top of a downward staircase beginning at the left and descending on the right. The child elements are towards the bottom of the stairs and the parent elements are at the top. This structure is effective when representing more complicated hierarchies where steps are not placed in obvious sequences. Further steps are concealed unless all of the steps are revealed in sequence. In the computer desktop example, a file that is being sought after can only be found once another file is opened. The link for the desired file is within another document. All the steps must be completed until the final destination is reached. Informal representation. In plain English, a hierarchy can be thought of as a set in which no element is superior to itself, and one element, the hierarch, is superior to all of the other elements in the set. The first requirement is also interpreted to mean that a hierarchy can have no circular relationships. The association between two objects is always transitive. The second requirement asserts that a hierarchy must have a leader or root that is common to all of the objects. Mathematical representation. Mathematically, in its most general form, a hierarchy is a partially ordered set or poset. The system in this case is the entire poset, which is constituted of elements. Within this system, each element shares a particular unambiguous property. Objects with the same property value are grouped together, and each of those resulting levels is referred to as a class. Hierarchy is particularly used to refer to a POSIT in which the classes are organized in terms of increasing complexity. Operations such as addition, subtraction, multiplication and division are often performed in a certain sequence or order. Usually, addition and subtraction are performed after multiplication and division has already been applied to a problem. The use of parentheses is also a representation of hierarchy, for they show which operation is to be done prior to the following ones. For example, times. In this problem, typically one would multiply 5 by 7 first based on the rules of mathematical hierarchy. But where the parentheses are placed, one will know to do the operations within the parentheses first before continuing on with the problem. These rules are largely dominant in algebraic problems, ones that include several steps in order to solve. The use of hierarchy in mathematics is beneficial in order to quickly and efficiently solve a problem without having to go through the process of slowly dissecting the problem. Most of these rules are now known as the proper way into solving certain equations. Subtypes. Nested hierarchy. A nested hierarchy or inclusion hierarchy is a hierarchical ordering of nested sets. The concept of nesting is exemplified in Russian matryoshka dolls. Each doll is encompassed by another doll, all the way to the outer doll. The outer doll holds all of the inner dolls, the next outer doll holds all the remaining inner dolls, and so on. Matryoshkas represent a nested hierarchy where each level contains only one object, i.e., there is only one of each size of doll. A generalized nested hierarchy allows for multiple objects within levels, but with each object having only one parent at each level. The general concept is both demonstrated and mathematically formulated in the following example. A square can always also be referred to as a quadrilateral, polygon or shape. In this way, it is a hierarchy. However, consider the set of polygons using this classification. A square can only be a quadrilateral. It can never be a triangle, hexagon, etc. Nested hierarchies are the organizational schemes behind taxonomies and systematic classifications. For example, using the original Linnean taxonomy, a human can be formulated as. Taxonomies may change frequently, but the underlying concept of nested hierarchies is always the same. In many programming taxonomies and syntax models, nested hierarchies, including Russian dolls, are also used to illustrate the properties of self-similarity and recursion. Recursion itself is included as a subset of hierarchical programming, and recursive thinking can be synonymous with a form of hierarchical thinking and logic. Containment hierarchy. A containment hierarchy is a direct extrapolation of the nested hierarchy concept. All of the ordered sets are still nested, but every set must be strict. No two sets can be identical. The shapes example above can be modified to demonstrate this. The notation means X is a subset of Y but is not equal to Y. A general example of a containment hierarchy is demonstrated in class inheritance in object-oriented programming. Two types of containment hierarchies are the substantive containment hierarchy and the compositional containment hierarchy. A substantive hierarchy subsumes its children, and a compositional hierarchy is composed of its children. A hierarchy can also be both substantive and compositional. Substantive containment hierarchy. A substantive containment hierarchy is a classification of object classes from the general to the specific. Other names for this type of hierarchy are taxonomic hierarchy and is-a hierarchy. The last term describes the relationship between each level. A lower-level object is a member of the higher class. The taxonomical structure outlined above is a substantive containment hierarchy. Using again the example of Linnean taxonomy, it can be seen that an object that is part of the level Mammalia is a member of the level Animalia. More specifically, a human is a primate. a primate is a mammal, and so on. A substantive hierarchy can also be defined abstractly as a hierarchy of concepts. For example, with the Linnean hierarchy outlined above, an entity name like Animalia is a way to group all the species that fit the conceptualization of an animal. Compositional containment hierarchy. A compositional containment hierarchy is an ordering of the parts that make up a system. The system is composed of these parts. Most engineered structures, whether natural or artificial, can be broken down in this manner. The compositional hierarchy that every person encounters at every moment is the hierarchy of life. Every person can be reduced to organ systems, which are composed of organs, which are composed of tissues, which are composed of cells, which are composed of molecules, which are composed of atoms. In fact, the last two levels apply to all matter, at least at the macroscopic scale. Moreover, each of these levels inherit all the properties of their children. In this particular example, there are also emergent properties, functions that are not seen at the lower level, and a scalar quality. Both of these concepts commonly exist in compositional hierarchies, but they are not a required general property. These level hierarchies are characterized by bidirectional causation. Upward causation involves lower-level entities causing some property of a higher-level entity. Children entities may interact to yield parent entities, and parents are composed at least partly by their children. Downward causation refers to the effect that the incorporation of entity X into a higher-level entity can have on X's properties and interactions. Furthermore, the entities found at each level are autonomous.